This is a short follow-up of problem 9.46 which we have done for the case of steam. We must now do the actual problem, which is the compressed air. So the facts remain the same, only the way of calculation will be different. Okay, the facts remain the same, only the way of calculation will remain different. So for an ideal gas, a reversible adiabatic process leads to PV raised to gamma equal to constant. We have proved this in class. It is very easy to prove. Okay. For this, we have the information about the pressure and the temperature and the intermediate pressure only. So we must use this particular relationship to find out the temperature. So PV raised to gamma equal to constant, and we have PV equal to RT. So we must obtain the relationship in terms of P and T. So P T raised to gamma by P raised to gamma R raised to gamma equal to constant. This R raised to gamma we can absorb in this. So P T raised to gamma by 1 minus gamma is equal to constant. Therefore P1 T1 raised to 1 minus gamma by 1 minus gamma equal to P2 T2 raised to gamma by 1 minus gamma, where gamma is equal to Cp by Cv. Okay, gamma is equal to Cp by Cv. What is the approximate value of gamma? Gamma equal to Cp air by Cv air fair. Cp air is equal to Cp of air at T equal to 20. Cv of air equal to Cv of air at T equal to 20. Let's see what. So the gamma is 1.4. This is well known. So the gamma for air 1.4. You might remember this from your JEE days. Okay. So P1 is equal to 100 kilopascal. Because we are now using the ideal gas equations, I would like to have the units remain more or less in the MKS system. 20 plus 273.16. P2 on the other hand is equal to 500 times 183. So T2 is equal to T1 times P1 by P2 raised to what thing is it? 1 minus gamma by gamma. Okay. So what is the intermediate temperature? So the intermediate temperature is 464.4 degrees Celsius. So the intermediate temperature is obtained as 464.4 Kelvin. Okay. So the initial temperature was 20 degrees at 293 Kelvin. It got because the air was pushed to a higher pressure, the temperature of air increased to 464, after which it is cooled from 464.4 Kelvin to 30 degrees Celsius, which is 303 Kelvin. So we can now easily find out the work done in the compressor, where WC equal to Cp T1 minus T2. Similarly, the heat transfer is equal to, so this is to be multiplied by the m dot, and the heat transfer Q dot is equal to Cp T3 minus T2 multiplied by m dot. So instead of having to find the properties, we simply use the ideal gas equation. So the W dot compressor is equal to mass m dot multiplied by Cp air multiplied by T1 minus T2 Q dot is equal to m dot multiplied by Cp air multiplied by T3 minus T2. M dot is equal to 0.5 kg per second. Oops, we have not defined what is T3. T3 is given as 30 degrees Celsius. So the work done on the system, which is the work done on the compressor, is 85.97 kilowatt, and the heat rejected from the system is 80.95 kilowatt.